So in this case, we are going to consider our AC theory, which is the part of the three-phase balanced loads, which is the part that is being actually introduced as part of the new curriculum. So if you are to consider going back to the question papers that you had before, you'll find out that we actually do not have even questions that are specifically on this part of the three-phase balanced loads. But that does not mean that we are not going to have questions in the future. We do not know, as this part has been introduced. I talked about it. Make sure that you go through the April 2025 exam preparations. I talked about that, the issue of question papers. You know, as your department will be introducing something, they will be actually trying to, like, it's a stage by stage. So we do not know, is it going to affect us this time? Is it going to affect for those who will be for next year exams? We do not know, but that is part of our syllabus. So we need to actually know this section of our AC theory, which is the part of the three-phase balanced loads. So if you're to consider the part of the three-phase, as we have the connections that are in three-phase, we do understand that three-phase loads can either be in star or in delta. As you consider the three-phase, they can either be in what? In star or in delta. In star or delta. So these are the major connections that you're going to have. All right, so a star connection can just be given in short like this for the representation of what? Of a star, then a delta connection in that matter. So these are the two connections that we can have. And these two connections, which is in star or in delta, can be found as balanced or unbalanced loads. So they can be classified as two, balanced or unbalanced. So we have the part of balanced and unbalanced. So in the major case of our question, for this introduction, we're gonna focusing with the balanced loads, and specifically, I'm going to major on the star connected loads. We're going to talk about that later on. So that is the part that we need, guys, to understand as we are having this syllabus. We've got two parts, the balanced and what? The unbalanced. So what is it, guys, that we consider as balanced? That is another part to talk about later on. These three-phase loads, as they are, before we talk about being balanced or unbalanced, the three-phase on their own, the three-phase connection, the three-phase connections. As we have a three-phase connection, what is our understanding? Yes, we have the star and the delta, which is the major part that we know. But remember that connections that are under a three-phase, they are being separated by what? 120 degrees. Remember this in your normal consideration. And as you have these, we are going to consider the sequence that you're going to have in terms of the voltages, the currents that you're going to have, which is the phase sequence. So as you consider them, these connections being separated by 120 degrees, they follow a certain sequence. So it is best for you to understand this before we consider our connections later on. So that is another part, all right, which is understanding of our vector diagrams. So the vector diagram is also important for us to consider. Like I said, our connections, they're being separated by what? 120 degrees. So as you have your phasor diagram under three-phase connections, we are going to use the phase sequence red, yellow, blue. So this is the phase sequence that we are going to to follow. All right, let me have this one, our phase sequence. The phase sequence that you're going to use in representing our voltages, our currents, whatever that way. Phase sequence, red, yellow, blue. All right, so we've got red, yellow, and blue. So this is what I want you to see here. We said this is a phase sequence that you follow, but there must be a reference. Where are we starting from? Remember, in terms of the vector diagram, let's say we've got this horizontal line. This is our reference at what? At 0 degrees, we are on the reference. So we want to know which part of the voltages is going to lie on the reference. So you'll be given a consideration to take red as a reference. Taking as reference. So we are going to be taking VR as reference. So this is what I want you to see, guys. If we are to consider VR as our reference, so this is something that you're going to be using. Please take note. In our syllabus, in our consideration, we are going to be using this. Our first sequence, red, yellow, blue, we take VR as our reference. So if you have this, like I said, this is a connection that this is the part that is going to affect any part of a three-phase. You are in star, you are in delta. This is part of what? Any three-phase connection. So this is what we have using this sequence. So we're going to have our red in the what? Reference. So this is where we're going to have our VR. All right. So let's just separate. Remember your quadrants, guys. As we have our quadrants, the angles that are being taken in this direction anti-clockwise, they are taken as what? Positive. Our angles will be taken as what? As positive. And that is the direction of our rotation. That was direction of what? Of our rotation. So as we are taking, our angles will be going that way. The rotation, not to say, okay, this is it, guys. When we say this is the direction that we are going to take, or the rotation, we are simply saying that's our normal. Let me present this way so that we understand each other. That's our normal. As we go this way, positive, meaning to say it can be reversed in terms of the angles. It can be reversed this way. There will be negative angles. All right. So I want you not to be confused with this part that I'm going to also present at the same time. In this direction, we are saying these angles, they are negative, which is true. But also this direction, it presents or it represents the phase sequence. For phase sequence, the way that we take our voltages, like red, yellow, blue, like the way that we have our sequence. So this direction is for the what? Is for the phase. So this is also phase sequence. For phase sequence, you take this direction. In terms of the angles, guys, the normal rotation is this one. Anti-clockwise, that's your angles are what? Positive. But it does not mean you cannot rotate this way. No, you can rotate that way, but your angles will be taken as what? As negative. But in terms of the normal presentation, this clockwise, this part, in terms of the normal presentation, it is representing what? The phase sequence. So meaning to say, we are having red, yellow, blue in that way. This is the way that we take our sequence, red, yellow, blue. So if red is here and we say they are separated by 120, it means yellow is going to be somewhere. Remember these quadrants, guys, 90, 90, 90. So 120 degrees can be somewhere there after 90 degrees. So it's just somewhere here. So this is where we're going to have, like we said, red followed by what? By yellow. So this is where we're going to have our yellow. This is for the voltage. Separated by 120, remember, 120 degrees, more than 90 degrees. So this is 120. But we are going, look now in terms of how you take your angles, it will be negative 120. Here we are following the phase sequence to say we follow this way. But in terms of the angle, is what? A negative angle is opposing the normal rotation of what? The angles. All right. We move again in that way, phase sequence like this. We are going this way. So we are going to have another 120 separated. So guys, as we can see, according to our angles, if this is 120 degrees, what does it mean? It means the remaining angle here will be 60 degrees. From where? Angles on a straight line, they add up to 180 degrees. So it's going to be 180 minus 120, which is what? 60 degrees. So there is a 60 degrees that is remaining here. But we need what? 120. So to obtain 120, it means we are going to need another 60 degrees there in this quadrant for us to have what? 120. So it means another voltage will be somewhere like this. It's going to be somewhere there. So meaning to say the whole of this angle combined together is the one that we need, which is what? The 120 degrees. So it means there's a 60 here, there's a 60 here to make that 120. But as we are not worried about to say there's a 60 there, we are worried about the whole of that angle in between. It's 120 degrees. So like we said, red, yellow, where are we going? To blue. Red, yellow, blue. So that voltage is for what? For blue. So that's how you're going to present all three phases. All three phases. It is only going to change in terms of the presentation to say when we are in star, there is a way of presenting voltages that are in what? In star, or even the currents that are in star. There's a way that you present them. But how you separate your voltage is going to be like this. They'll be separated by what? 120. So meaning to say the remaining part here will be 120. Remember, we said there's a 60 here that is remaining. So what does it mean? It means we're going to have 30 degrees to make the 90. So the 90 here and the 30 degrees will give us what? 120 degrees. So just like that, 120, 120, 120, like that. So this is what we have. So this is our red. In this sequence, red, yellow, blue. Red on the reference. Red as reference. The sequence, red, yellow, blue. Phase sequence, just like that. All right, so that is what you're going to have. And in terms of the currents, remember when you talk of the current, it is about how it is affected to the voltage. The current, when you talk about the issue of lagging or leading, depending with the connection, the load that you have, is it an inductive load? We know that inductive loads, when it is an inductive, that is where we have what? A lagging power factor. You've got an inductive motor, lagging power factor. Capacitive, these have got what? A leading power factor. They will be having what? A leading power factor. So as we have these guys, they are going to affect in terms of our currents to say, let us say in terms of the leading and lagging part, because red will be affected with its current for red. So if its current for red is here, let's say the current for red, we want to consider to say where red is. And let's say its current is here for red. Let's say this is where its current is. Comparing current to the voltage, we are saying this current for red is what? Is lagging VR. It is below. So we are going to be considering the angle that is between. If it is red, it must be of red, yellow to yellow, blue to blue. So we're going to see that in our next part of our presentation. But this is what I want you to see about the issue of lagging and leading. We said it's current. You compare current. Is it current, lagging, voltage, current lags voltage, or current leads voltage? So we're going to present in that manner so that we do not have a confusion. So if it is a consideration, let's say we've got something, I'm just going to put something clear let's say we say this is our reference at what? At 0 degrees. I'm just going to use our VR at reference. All right. Let's say there's a current here, all right, which is called I1. And let's say there's a current here, which is called I2. These two currents are compared with the VR red, our red there on the reference at what? 0 degrees. So current, it's either it lags or leads the voltage. So let's compare. Let's start with I1. When it is on top like this, compared to what we have, this is our VR here. I1 is on top. So it is the one that leads. I1 leads VR. In this case, we are saying I1 leads by V1 will be having what? Your phase angle there. So we are saying I1 leads VR. Take note, guys, it's on top. I2, it's below VR. So meaning to say I2 lags VR. It's below. What is on top is the one that is what? Leading. Below, it lags. That is how you consider. If they are in the same line like this, let's say I3, let's say there's a current here, which is called I3. We are saying I3 is in what? Is in phase. It will be in phase with what? With the VR. What does it mean? At 0, they are in line there at 0 degrees. It does not mean that it is only at 0 degrees. They can be like this, like voltage current here, in the same line. That is what being in phase, in the same line. In the same line. They're found in the same line. So if they are found in the same line, they are in phase. So this is the consideration that you just need. What is the presentation in terms of the current to the what? To the voltage. So I want us to consider this later on. Like I said, we'll need this later on. Or let me just leave it like that. It's not a problem. We'll consider it later on. Let's go back to what we had there. So as we have these guys, this will lead us to the balanced loads now. The balanced loads, which is the major part here that we want to talk about. Three-phase balanced loads. All right, let's talk about these loads, guys. Like I said, much we're going to add as we have our questions and revisions. We'll see that later on. What is it that we have when the loads are being balanced? Balanced. And these are in three phases. What is it about these loads? All right, no problem. Balanced three-phase load. So this is what we have. When balanced, there is the issue of being balanced and unbalanced. And when the loads are being balanced, they have something that they have in common in terms of the load itself. To say the impedances in phase will be the same. The currents in phase will be the same. So that is the issue of what? Of being balanced. We'll be having identical loads, identical impedances, same impedances. That is the issue of being balanced, same impedances. In terms of our presentation. So if we consider this in terms of our impedance, we're going to talk about that later on to say how is it this and that. But as we have the balanced three-phase loads, just like what we have, the three-phase can be what? In star or in delta. So in this case, our major class is going to be focused on the star-connected loads. So we're going to have the nodes of the star connected loads under what? Balance the three phase. All right. So this is the major part, guys. Do not forget we are working with what? Balanced loads. But as in star. As in star. So in star, we are going to consider, okay, let's consider the connection in star so that at least it can be, we can understand this part together. So remember your star connection, like I said, guys, it's just going to be like this. So we have our load here. So just going to have our load and also another part. So the issue of drawing, guys, I said about this, I think now you understand me, guys, that in terms of the drawings, I just draw that for you to see, or just for you to have the understanding, not to say this thing of good in drawing, guys, it's not for me. But you can just, you guys, you're supposed to draw nicer diagrams, actually. But as for me, I'm just going to make you to see what is happening there. All right, so this is what you're going to have in star as we have our connections, red, yellow, blue, red, yellow, blue. So the line connections, you'll be representing with a bar, the line connection. So this will be red line, which is our, just like we are considering the red conductor, the red line. So you consider with a bar like that. So like I said, we've got red and we've got our yellow and that's our blue in this case. So meaning say this part here, we are talking of what? Where we have the supply. So these are line voltages, all right? So we're going to have our supply and under a star connected, we have a neutral connection. We have a neutral, which we do not have in delta. So we must indicate a neutral in star, all right? So in star, we must have a neutral. So we're going to just have it like this. So let's say this is the part of our neutral here. So let me just put so that we do not mix a lot of things because we're going to need our voltages also. So let us just have our voltages. So these are line, like I said, this part here, line. These are line values, the ones that you see with this bar. So no problem. I'm going to talk about that later on, like in terms of. So you're just going to have a connection. So guys, here, just going to pardon me. So this is a line voltage, all right? So that's a line voltage. So let's put it here. And let's also have another line voltage, all right, which is going to be here connected to this one. All right, so these are considered in what? In line. And we also have line here between these two. Just going to have another line here. All right, so you guys, you can just use your textbook, like in terms of proper diagram. These are VL, VL, VL. All right, then as we consider the currents, this will be in line current. We have the part that is entering what? The red. This is red, but as our line, the same here. This is our yellow, but we are having this as what? As line current. All right, this is our blue. So we are having this as our line current again. Remember the connection that we have in star, that the currents are the same, because as we have this point, we are now going to the what? To the phase. We are now going to the phase. So the current that is entering, are we seeing that it is still the same current? So that is a phase value. The same here, it is entering the part of the yellow phase. It is still the same current that we had, phase value. So that's why we say in star, the currents, guys, are simply what? Are simply the same. So as we enter also this phase of what? Of blue, we are having our current in phase, the same current that we had as our line there. And that's it. So that's it, guys. Here we've got our star point. Do not forget your star point. The neutral, the line, the part of the neutral in terms of our star connection, there's a current there. So we also have to consider what? The neutral current. And the phase values can be presented. I want you to see this part because this is the part that is going to affect our connections to say we are in star, we are in delta. How you present your connections, it is here about our phase values. Remember I said the line value is going to just be using that bar like this one. So if it is like voltage, like let's say for the red phase, you'll be writing like this for line values. Line values, you'll be writing them like this, red. So you'll be having a bar like that, red, like this, like red phase. If it is yellow, red, yellow, blue, then we move on to the blue like that. So you'll be using a bar like this for the line values. All right. These are the line values. But as for the phase values now, this is the part that I said you must pay much concentration here because they are taken to the neutral. You take each phase to the neutral, meaning to say we take red to the neutral like this. We take red to the neutral. So it is our phase value, this one. This is a phase value. It is connected to what? To the neutral. So understanding this, guys, to say we are taking to the neutral, it means, all right? So it means as we consider the phase values, all right, as we consider phase values, we're just going to talk about this, guys, later on. Is it current or what? Yeah, I'm just a basic, all right, just of what you need to understand. Using the phase sequence that we had of what? Red, yellow, blue, like this. They are taken to the what? To the neutral, these phase values. So it means the one for red, it will be taken all, they'll be taken all to the neutral. So it will be Rn, Yn, Bn in this phase sequence. So meaning say under a star connection, our phase values will be given as what? As R to the what? Neutral. So Rn. If it is for the yellow, it will be Yn. If it is for the blue, it's going to be what? Bn. To the neutral. That is how you take your connections. Red, yellow, blue. Red to the neutral, yellow to the neutral, blue to the neutral. Those are what? Phase values, as you can see, to the neutral. Those are phase values. So it is the same here between yellow and what? Between yellow to the neutral. It's a phase value, this one. Yellow and what? Neutral. The same thing between what? The neutral, from the neutral here, going to the what? Going to the blue. That value that you have there, it's a phase value because it's connected to the neutral as it is connected to the neutral. But from a line to a line to those are line values, right? So this is how you take your phase values. So it can be current. If you want to talk about current in the red phase, you represent it like this. If you want to talk about current in the yellow phase, we talk about this one. We talk about current in the blue phase. That's how we're going to present our current. In what? In star. We are going to have another presentation again in delta because in delta, we do not have the neutral. So we cannot have them as Rn, Yn, Bn. There is going to be another format. So you need to know the format that you use. The format of a star, the format of what? Of a delta. So in this case, we are not in a star. All right, so that is what you're going to have, guys. And like I said before, the presentation of the currents from the voltages is going to depend with the load that you're working with because it can be having a lagging power factor, this and that. So we're going to see that one later on. So let us quickly rush to the calculations that we're going to need in a star. for a balanced three-phase load, the connections, the calculations that you're going to need, just one or two that you're going to need. So let us just list. So for voltages, guys, let us just start with the voltages. So calculations that we're going to need. So as of our calculations, the first part for the voltages, all right? So just gonna need calculations for what? Voltages. So in this case, we do not have much because we saw that our voltages can be presented in what? As line values and as phase values. So in what? In star, as we considered, guys, remember we are in what? In star. We are still in star. All this part that we're going to have in this class is going to be on star. So for phase values, so, all right, let's just see here. For phase values, use, so we saw that as a phase values, using the phase sequence of red, yellow, blue, we are going to have our voltages as what? V for red, it will be Rn, all right? For yellow, it will be what? VYN, and for blue, it's going to be what? VBN. So that's how you indicate your voltages for phase values. If they are phase values using our phase sequence of what? Red, yellow, blue. So we're going to follow that red, yellow, blue. Then we consider for line values. So for line values, we're going to use, remember I said if it is red, you present with a bar like that. So it's going to be red like this. So for yellow, that's yellow for the yellow phase. All right, so you're going to present like this with a bar. And for the blue, so it's going to be VB like this with a bar. So this is what we have. So this is how you present your voltages. But do not forget that you are in what? In star. Where in star we do understand that VL is equal to what? The square root of 3 VP. Remember your voltages. So therefore, VP as a phase value can be calculated from VL, which is what? VL over what? Over the square root of 3. So take note about this VL. So remembering, guys, that we said our angles, they are separated by 120. So your vector diagram here is going to play a role. Where did I put that vector diagrams on top? Remember here, your vector diagram here that we had. It's going to affect even these voltages because we say they are separate 120, 120, like that. So if you consider red is at what? 0 degrees. Yellow, this one, is at what? 120, which is negative 120. Remember, I talked about this if you are going this way, negative. Blue, it's where? Positive 120. So that part, I want you to take it as it is from that consideration. You see that these voltages that we are having here, they'll be presented. We're going to have our red there. It means red, as we saw, guys, it's at what? At 0 degrees. So it simply means it's VP at 0 degrees. The phase value, this VP that we calculated here from the phase value, this one. This one is from the line value that you be given. You calculate your VP. This is the one that we need here. So in the same sense, if you following that sequence, red, yellow, going to the yellow, guys, we saw that where yellow is, okay, let me put it this way. It was like this. This is where we have what? Red. So it's going to be like this. Red, yellow will be this side. This is where we have our yellow and our blue. This is where we have our blue, as in what? we are considering three-phase connection in what? In star, separated by 120 degrees, remember. So this is what we had. So we are going to notice that yellow, this one, for yellow, it's negative 120. So this is what? VP negative what? 120 degrees. Moving on to blue, these are phase values. Remember, we're talking about what? Phase values. So it's going to be VP at an angle of what? So this is from red, it's what? 120 degrees positive. This one is positive 120 degrees. So this is how you're going to take all your voltages, guys, all your phase values. These are phase values. Remember, we're talking about these phase values. That's how you're going to take them, all of them, guys, as you consider what? Your star connection. Even in delta, the only difference will be here on the presentation to say in star, we use what? We take our connections to the neutral. So red to be taken to the neutral, yellow to the neutral, blue to the neutral. But this is our phase sequence, red, yellow, blue. Always, these angles are not going to change, guys, because we said red is on the what? Reference at what? At 0 degrees. That part is not going to change always. So this is how you take your angles, always. It's not going to change. It's not going to change, right? So as you can see, they are different in terms of their angles, but same VP, the same VP that you calculated here. It's the same. All right. I think, guys, we add some of these when we are doing calculations. I think that'll be best if we are working with what calculations. I'll be adding more information. So that is for the voltages. All right. Let's move on to the currents in what? In a star balanced load. All right. So that's the first part was this one. Let's move on to currents. All right. So for currents, we still have the same thing, guys, just like our previous presentation. Phase values. All right. For phase values in star, we are going to be using same concept. We said RN like that. So means say our currents will be taking a what? Red, yellow, blue. So that's red, yellow, and blue. So that is how you're going to be having your currents. Same as what? Your voltages. Same consideration in terms of taken to the neutral. All right. So this is it in star. But as we do understand, the major part of being in star is that the values are the same. The line value is equivalent to the what? To the phase values. So meaning to say, if you're given a line current, we have got what? A phase value from there. So there's nothing much there. Then the line values, as we have here, guys, this one is just going to be the same. Let us just write. All right. So just like we had here, these ones. So it will be for the red line. All right. The yellow and the blue, just like that. So that's how you present your currents, which are line values in terms of your calculations. But remember, we are saying these currents are the same. In our normal presentation, line current is equal to what? Phase current. So if we understand that line current is equal to the phase current, it simply means the phase current is equal to what? Phase current is equal to line current. That is what it simply means. So therefore, with this understanding, as for our balance, the part of being balanced now, the importance of being balanced, we said these loads, they have what? Same currents drawn from the supply by the what? By the phases. The phases, they're the same. In terms of the phases, they're the same. The phases, like the phase values that will be having here, they'll be the same. But these phase values now, these ones, guys, we are saying it's a presentation. It's to be calculated. They are to be calculated, this one. Do not, Okay, let me write it this way. Do not forget, guys. Do not what can I say? Do not confuse the normal present. This is just a normal presentation of where when you are just saying you are in what? You are in star. You are in a star connection. Line current is equal to phase. So using that, I want you to take it now that way to say, these are phase values, these ones. And these are what? Line values. So you're simply saying these two, they're the same. The phase value, all right? So let me just save here, phase values. So we're going to have phase values down here, going down, and we're going to have what? Line values this side. So you're simply saying these two, they're equal. The phase and the line, they are the same. So meaning to say, red is equal to this one, red again. The red of a line, the red of a phase. The yellow of a phase, it simply means it is equal to the yellow of what? A line. The blue of a phase is equal to what? The blue of a line. That is what it simply means. Phase values are equal to the line values. But these phase values, they can be determined, these ones. Okay, let me put it, we still have space here. These phase values, they can be determined from the voltages that we had here in what? In phase. Remember, we said these are phase values, these ones. In what? In phase. So using these phase values, this phase value for red, the phase value for yellow, for blue, with their impedances, we can calculate these currents. So it therefore follows that thus red can be calculated from what? For phase values. Remember here, for phase values, guys. Let me just rewrite. Let me just rewrite. For phase values, the red phase will be equal to the voltage in red over the impede corresponding to red. We are still red. So it must be impedance in red phase. That is what it means. It also follows that for the yellow, the current that we have there in yellow must be equal to the voltage that we obtain from that yellow phase, from that yellow over the what? The impedance of that yellow. It also follows that if I am to calculate the current that is in the blue phase, I'm supposed to use what? I'm supposed to use its corresponding voltage in the blue phase to its impedance in that same blue phase. With these currents can be determined, each can be determined for balanced loads. And these currents together, they add up to the neutral current. So this gives us the neutral current. We therefore conclude that the neutral current, which is the sum of these. Using our phase sequence of red, yellow, blue, so we're going to add red plus yellow. Remember those connections to the neutral, guys. They were connected to the neutral. So that's why we have to take the phase values. The yellow plus the blue. That is how we are going to have our neutral current. But since this is a balanced load that we have, this value of the neutral current is going to be equal to 0. For what? Balanced load. That is what we have there. We're dealing what? With a balanced load. It'll be equal to 0. So they can actually give you questions to prove that. So you just have to calculate these values. You have to find this, find this, find this. Addition, we do know, guys, mathematically, as we consider addition in what? In rectangular form. So meaning to say these, we are back to the J notation. And as you consider to say for the J notation, what does it mean? It means these are supposed to be represented with their angles in phase. With their, that's why you saw that we had those B, whatever that BN. They have their angles there. They have their angles. So we are talking about the J notation, complex numbers, as you can see. Polar form. There's a part of polar form. Polar form is going to play the major role where? On this part. Division. This division here. To be best for you to do this one in what? In polar. We saw that in our mathematics. Addition. Rectangular form. So that is what you're going to have. We just need to work out as many questions as we can. Just try to figure out, like I said, so far, this is a new part that is being introduced. So we are going to work with more questions from textbooks. Because as for question papers, we do not have any question paper right now that has these questions. So we are going to work with our textbooks and so on. So that's it, guys, for the neutral current. Still under a star connection that we have as a balanced load, they can ask us to calculate power. Or let's just have impedance, then we consider the power later on, since we already have this part of the impedance that we have. So let's just talk of the impedances. So for impedances, as we have these balanced loads, the part of the load is on the impedance. That is our load. So the part of that load, it can be inductive, capacitive, whatever that we have there, but they are balanced, same. So the first thing, the presentation, still the same as we had. Okay, let's talk about that. But this one, I think now we are used to, guys. As for the impedances, we work with what? Phase values. The impedance that you are given, it will be a phase value. All right, you work with what? Phase values. So meaning to say, if I am to given the impedances as phase values, considering red, yellow, blue, we are going to be having this as what? As red. Then we're going to have what? Yellow and what? And blue. So these are the ones that we have under a star, working with a star for our balanced load. That is how we're going to be presenting our impedances. But the impedances, guys, I want us to be very, very careful about these impedances, because that is where our major part is. As we can see, we have that impedance here on the calculation of the phase current. So please take note, it must be a phase value. So whatever value that you be given in exam, it will be a phase value for what? For the impedances. All right. So as they are phase values, following a phase sequence of red, yellow, blue, the one that we had, it follows that normally, according to the load that we are given, our load can be inductive, meaning to say it has a lagging power factor. I want us to be very careful there. For a condition that we have a lagging power factor, it means we have what? An inductive load. That's an inductive load that we are having there. So as you have an inductive load and you want to present an impedance, how do you present our impedance? Remember, guys, our Z is equal to R plus or minus JX. When it is inductive, how are you presenting this? You're adding, was R plus JXL. This is what we are presenting. Inductive. Remember that part, guys. Those inductive loads, guys, they had the lagging power factor. So as we can see, it is affecting part of we are not talking about power factor. But it's going to the impedance, because the presentation, because you are dealing with what? An inductive load. So as a phase value, these are phase values. I'm just going to put P here. I put a P here, I put a P here to show that we have got what? Phase values. So from that Z, our impedance, I have what? Resistance. I also have the reactance of the inductor. I have the reactance of the inductor, which can give us the inductance there. Remember that this is equivalent to 2 pi FL from our N4 there. Okay, so that is something that you just need to put into consideration. A lagging power factor, your load is inductive. So the presentation of the impedance is affected. Same with a leading power factor. So if I have a leading power factor, capacitive load this time, and thus it is going to affect our impedance at the end, capacitive. Our ZP is going to be what? RP minus JX, that will be CP, capacitive. The P, it is just for phase values. We are using phase values. So that is what I want you to put into consideration as you are working with your impedances, and these are phase values. So you must know you're dealing with a leading power factor. The presentation of the impedance is going to be like this. And like I said, we are dealing with balanced load. These are the loads that we talk about. So these impedances, they are the same. For balanced loads, it simply follows that the impedance for the red phase is equal to the impedance of the yellow phase is equal to the impedance of what? The blue phase, just like that. So with this, yeah, guys, as you can see, it's J notation. You need to know conversion, polar form, rectangular form. I talked about those conversions, so make sure that you go through. But guys, as you're in N5 now, you must be knowing how to use your calculator to do those conversions. So make sure you go through those conversions and just also understanding of the power in three-phase calculation. All right, we have to add that one. Then we finish, guys. We've got a lot of things now. I never thought you're going to have this because we need to do examples in the next class that we're going to have. So let us quickly look into the power. All right. So for the powers that we have under our three-phase, still with the balanced load that we're going to have, we consider to say we are in star, also that part, but the star connection part, guys, is not going to affect us to say, okay, we are in star, but in terms of being balanced, these powers will be the same. The presentation still the same, just like what we had previously. So we are going to be using phase values to present our power. We use what? Phase values. So guys, it will be just that same consideration for the red, for the yellow, and for the what? For the blue, guys. We've talked about this just for the sake of time. So these are phase values what? For the balanced load that you'll be having. So we have got the same power. This is the major part that we have. The power is the same, meaning to say the power that we have for red phase is the same as the power for the yellow phase. It is the same as the power for the blue phase. It is the same, the power. So if we want to calculate the total power, we can simply add these, meaning to say it's red plus yellow plus blue. But guys, we are saying these are the same. So it's simply like, let's say one of these is equal to P1. Let's say one of these is equal to P1. P1 represents one of the given powers. One of the given powers. one of the given powers. Any one of these. Let's say P1 represents. So it simply means the total power is equal to a 3P1. If I have one power, guys, it's simply multiplied by 3 because they are the same. All right. But in a normal consideration, because it's not always, or it might not be given these, how can I calculate the power? Normally, in a three-phase, guys, we know our calculations. Remember that the power, if you're using phase values, is 3 times VP IP times what? The power factor. Under a normal three-phase calculation, you're supposed to know this formula for power, the true power. Or it can be calculated from what? The square root of 3 VL IL cos of phi, if you are considering what? The line values. That is it. And this is for the phase values. Just like that. So meaning to say, if we are to consider our total power, we can calculate from this so many formulas, guys, for power that we can use and also know the types of power. This is the true power that we have. As you consider the power, guys, that we have got the true power, which is P, and that's the square root of 3 VL IL cos of what? Cos of phi, like that. We've got the apparent power, voltage times what? Voltage times current, but it will be what? Square root of 3 voltage times current. We've got the reactive power, square root of 3 VL IL sine of what? Sine of phi, like that. So you also need to know the type of power that you have in your syllabus. And all those calculations, guys, the power factor is equal to the true power over apparent power. All those, we are still on calculation of what? We are still talking about power, guys. So it does not go aside. As you are to deal with power, it means it's part of your calculations. So as a conclusion to all this part that we had, I want you to put in mind that as of the balanced loads, as we are going to be having our calculations from this part, we are going to be dealing with calculations. So we can conclude that as a conclusion, under three-phase balanced, actually not to say in star or delta, this one is not about, but we're going to just summarize in what? In star. So we are going to consider these importance, the very, very important that we have. Impedances, simply the same. The impedances of the phases, considering what? Each phase. All right. So we say the impedances of the phases, right, are equal. So if you consider impedances that are of the phases, they are equal. These are impedances of those ZP phase. All right. The currents also, the currents which are drawn from the supply by the phases, take note, by the phases. All right. So the currents drawn from supply by the phases are equal. All right. So this is considering what? In our star connection, very, very important for you to note. And also you saw that the power is the same. So in your calculations, you also considered and saw that the power drawn by the phases are equal. The power drawn by the phases are equal. Another part that you also need to put into consideration. And also the neutral current, as we had, guys, in star, we saw that the neutral current is equal to 0. The neutral current is equal to 0. We are talking about what? a conclusion of what we saw on our balanced, on our, let's say, three-phase, sorry for that, three-phase balanced star connected loads. So the major part here, that is it. So guys, let us meet in another class doing questions. And what you just need is to also follow your membership classes so that you do not miss any of the other classes that you're going to have in terms of the preparations, working with examples, as we shall be working with more questions. From these introductions, we need questions. We have the formulas that are necessary. It is not just about the exam. You also need to know how to answer questions from examples, this and that. So for you not to miss those classes, make sure that you become part of membership. Your classes will be presented, and also to follow the playlist so that you see the classes that are there in the playlist, which is for this one, for the three-phase balanced loads. So that is it, guys. Till we meet again.